Good evening. Welcome, ladies and gentlemen. Welcome to this Foundation for Science and Technology event on the use of AI in the early detection of disease. Welcome to our participants here physically in the Royal Society, and also to our participants who are joining us online. And for those who are joining us online, just to remind you, for those who are following on Zoom, do please use, you're very welcome, encouraged to put in questions. Do use the Q&A function for that, please, not the chat function. And of course, you can upvote questions that you strongly support, which does help us identify the key themes to pursue in question and answer. We're also on the hashtag FSTAI disease if you want to tweet about the event. And of course, AI is a very hot topic at the moment. There's a lot going on. And rather than trying to sort of boil the ocean and cover everything that's happening in the world of AI, we decided particularly to focus on the really exciting recent developments on the applications of AI to early detections of diseases such as cancer, Alzheimer's, retinal diseases. And we're going to hear from 4 experts. Our first speaker is David Crosby. We're then, and I'm going to introduce them, subsequent to him, going to hear from Mike Oldham, from Jessica Morley, and I must apologize to Jessica for the misspelling of her name, and she has corrected it, so we know how it should be spelt, so that's great, and thank you so much, Jessica, for keeping us to high standards. We expect the FST, and then we'll hear from Tobias Rijken. But first, let me begin with David Crosby, Head of Prevention and Early Detection Research at Cancer Research UK. Did his PhD studying cell signaling in platelets. He has spent time in academia, in industry, and joined the MRC before joining Cancer Research UK. So over to David Crosby.
Thank you very much. Thank you very much, David. Thank you, Gavin, and the organisers for having me here today. It's a pleasure to be here. So I'm going to spend my 10 minutes slidelessly espousing the virtues and the kind of excitement and the positivity that I feel towards the application of AI in the early detection of disease. So, as David said in the intro, I work for Cancer Research UK, so that's the context for my positioning here. I'm the Head of Prevention and Early Detection Research there. I should also say I'm currently on secondment part-time, 2 days a week, working for the government in the Office of Life Sciences. And I'm obliged to tell you all that the views I'm about to put forward are my own, and they're certainly not representative of His Majesty's government. So, with that said, the early detection of disease, for me, is built around 3 key issues. The first being, who do you test? And that's a matter generally of understanding risk. The second is, how do you test? And that's a matter of technology. And then the third is, what is it you're testing for? And what have you actually found once you've found it? And how do you deal with that? And that, for me, is a matter of biological insight informing clinical decision making. And I think that AI is set to have a major impact on all 3 of those domains. And in fact, as it's going to have an impact on pretty much every aspect of human life. So, you know, my context, the way I come at this is I'm fundamentally a technology optimist, and I feel like it's inevitable that AI is going to impact, you know, most aspects of human existence. In the same way as many other, you know, technological advancements have throughout human history, and you know, I think this is probably going to be of the order of magnitude of things like the agricultural revolution and the industrial revolution. You know, it's going to change the way we live, and you know, there aren't a lot of people working with abacuses or looms anymore, and you know, human employment and human input is going to change. And change doesn't necessarily mean obsolescence, and it doesn't necessarily mean bad. It means different. So that's my sort of umbrella statement. Now, within that, let's look at the early detection of cancer. There's a few areas which are already being impacted by AI in the way that science is conducted and the way that clinical care is delivered. And those I'm going to cluster in, I think, 3 broad areas. One being risk, one being the sort of biological and biomarker side of things, so blood tests and the like, and then one being imaging. And imaging covering both the kind of gross anatomical imaging like X-rays, CT scans, MRI scans, but also imaging on the microscopic level. So, when you take biopsies and look at pathology slides. So if we start with that first area, there's a ton of research that's been ongoing for, years now. And there's already a lot of evidence to show that AI and machine learning approaches can be trained to replicate the function of, for example, a pathologist. So when you take a biopsy of a potential tumour at the moment, and you look at that down a slide, it's been stained, the pathologist reads it, and makes a judgment, is this cancer or not? And that judgment is based on their assessment of that visual pattern that they can see before them. Are there cells penetrating through membranes where they should not be penetrating? Are there clusters of cells that are behaving in an unusual way for the type of cell that they should be? And what the pathologist is doing there is pattern recognition. And of course, AI is a pattern recognition engine, as is the human brain. And so you can train up the machine to essentially replicate the judgments that humans make. Now, the problem with the machine is it's only as good as the human judgments, and the problem with the human judgments is that they are inherently flawed also. So no disrespect to any pathologists or indeed radiologists in the room, but their judgment is not perfect. They can only perceive what they can perceive, and so there are always small things missed and things misinterpreted and perhaps over-extrapolated. But also there's an issue of reproducibility between individuals. A different pathologist will look at the same thing and give a different judgment. There's also demonstrable evidence in literature of variability within individuals. So a given radiologist at any given moment of the day could make a different judgment from the same scan. So the hope is that the machines actually won't just be replicating what human performance can achieve, but actually can transcend it and eliminate variability and subjectivity, based on the time of day, or how tired they feel, or how many scans they've just had to sit through. And that's something I think that applies to all of those sort of image-based recognition areas, and be that looking at an MRI scan, being it looking at a pathology slide, being it looking down a camera through an endoscope at a tube inside of your lungs or colon. And there are data already showing that we're matching human performance, and the hope is we can exceed it. And there'll be other technological advancements that can synergize with AI approaches. So, for example, with early detection of colorectal cancer, the first line is a test of the feces to see if there's blood in it. If you have that, then you're referred for a colonoscopy. And at the moment, that's a very manual process. It's a camera on a tube that's interpreted by a human looking down it, who may or may not spot anything suspicious. There are technologies like a capsule endoscopy now, the way you can swallow a miniaturized camera in a pellet that then passes down through the colon, that gives continual video surveillance of the colon as it passes through. And AI approaches then can be used to sort of do the spotting of hours of footage that a human couldn't realistically do. So you can get a more complete picture with a combination of technologies than you can from the standard approaches alone. Moving beyond imaging, the other big thing that's happening in the early detection of cancer at the moment is what are called multi-cancer early detection blood tests. I'm going to call these MCEDs for short, multi-cancer early detection. So these MCED tests, which you'll probably have read about in the newspaper, they key off of fragments of tumour DNA which circulate in the blood. So tumours are unstable things, they break down and they'll release their contents into the bloodstream. And their tumour DNA is subtly different in small ways from normal healthy DNA. But the fragments are so small and the concentrations are so low, it's quite difficult to spot. But the sequencing technology is advanced to the stage where it looks like that's a feasible way of doing early detection of cancer, with the advantage of a blood test being over a scan, over an endoscope. The advantage of the blood test being that you can assess for multiple different cancer types at the same time. So you could screen a given individual and be looking for lung cancer, brain cancer, toenail cancer at the same time, right? And that's a really exciting prospect if it works. There's a very large trial of one such technology happening in the NHS right now. And that technology has been evolving over the past 10 years or so. The technology originally came from looking at fetal genomic aberrations. So where you do a test for Down syndrome, and traditionally the test is ultrasound followed by amniocentesis, a needle into the amniotic fluid. That's now been superseded because you can find bits of the fetus DNA floating around the bloodstream. So we know there's proof of principle there. For cancer, much more complex. Every cancer is different. Every mutation is different. The patterns of subtle DNA alterations, there's thousands, tens, hundreds of thousands of permutations. So the reason that this blood test exists and the reason that it's in clinical trials right now is AI. The complexity that you were looking for across all of those tens of thousands of different alterations would have been imperceptible to a human. But the AI is what found the pattern that test is now looking for and analysing. So that's a clear example of something where we've jumped ahead beyond what humans were capable of. So that's happening now also. Then lastly, my third subject was about risk. So if we knew who was at elevated risk of developing cancer or indeed any other disease, then we could be potentially much better at early detection. So the premise being, any given disease is relatively rare in the general population. So if I tested everyone in this room right now for heart failure, for cancer, for Alzheimer's, one or two of you might have it and the rest wouldn't. But my test isn't perfect, so every now and again it's going to give a false positive. And because of the weight of numbers of people that you're testing, and all tests are imperfect, if you tested everybody for cancer every year, you'd have vastly more false positives than you would true positives. And that's a problem with any testing, any screening or early detection strategy. And so the hope is that early detection, that AI can help us refine that, make it slicker. And one way of doing that is by upping your incidence rate in the population you test by only testing people who are at elevated risk. But the question then is, who is at elevated risk? And that's complicated. And there are lots of individual silos of research where people are looking at different types of risk factors. So there are people who are interested in genomic risk of cancer. The genes that you were born with put you at different levels of risk. There are people who are interested in socioeconomic determinants of health. The town you're born in, the environment you grew up in, the pollution you were exposed to put you at a different level of risk. And there are people who are interested in behavioural risk. Your diet, your exercise, whether you smoke, these are also all risk factors. What AI might enable us to do is to integrate those. So that is an incredibly complex proposition because you're looking at thousands of variables in each of those arenas, and to model them all in together, again, I would suggest is beyond the capacity of a human mind. But that's where we're hoping that AI will also make a major impact in integrating multimodal data to assess who's at risk and who you should be testing in the first place. So that's the three main areas where I think we're going to have significant impact. The last two kind of cross-cutting themes I'll layer onto that are the kind of caveats, with one being, even once you've found something, that's not the end of the story, because a lot of disease can be inconsequential. So, for example, you could diagnose every single prostate cancer in every guy in this room, and there might be a couple, don't want to worry you, but many prostate cancers are inconsequential. They're growing so slowly that the individual with them will die of something else long before that prostate cancer was ever going to do them any harm. And if you built a machine that detected everything, then you'd be generating a huge treatment burden on the NHS, which may or may not actually have any impact on anyone's quality of life or longevity. So that's a big caveat to be aware of. And the other big caveat is stress and anxiety and psychological ramifications. And we have to think very carefully about what people want to know about their risk of disease and whether they have incipient disease, and whether we can advise them to actually be able to lower their risk or prevent that disease. So there are important ethical considerations around that also, which AI won't help us with or solve, but it's something that we're going to need to layer onto it as we think about the future of AI in early detection. Thank you.
Thank you very much, David. We now go on to Mike Oldham, who joined Alzheimer's Research UK in 2021 to lead their initiative on the early detection of neurodegenerative diseases, harnessing digital technologies. He's an engineer. He's worked on the Vaccine Manufacturing Innovation Centre at Harwell. He's worked at NPL. He's worked at Innovate UK on the important issue of creating the catapult network. So, Mike, thank you very much for joining us. Over to you.
Great. Thank you, everyone. Thank you for inviting us to come and talk tonight. It's a real pleasure to be here. So you know that already. Conversations about AI are everywhere in the news, and I think Alzheimer's, and particularly dementia, is one of the biggest health challenges that we're going to have in our generation. And so it's no surprise that things like AI and machine learning are being thrown at all of the Alzheimer's research in as much kind of volume as everybody can possibly muster at the moment. In terms of numbers, we're quoting the statistic, 1 in 2 people will have their lives devastated by dementia unless we change the ending at the moment. That's about 1 in 3 people will go on to develop dementia, and Alzheimer's accounts for about 2/3 of those numbers as we move forward. During the next decade, we really need to revolutionise the way we treat, diagnose, and prevent dementia. Treatment, I mean, you've all heard in the news, great news this year in terms of lecanemab and donanemab, first-generation treatments, drugs that are intended to strip amyloid out of the brains of patients, and they're showing positive, albeit quite modest, results slowing down cognitive decline. First generation, it's light at the end of the tunnel, and it's a really, really exciting time to be in dementia research. Still a lot to do. The one thing they're all pointing to is the importance of getting in there early, of early detection and early diagnosis. If you can't detect the disease, you can't treat the disease. So that's the first challenge we've got. And so early detection is an absolute key to actually unlocking all of the power of the future treatments that you hear about on the news. If we talk about where we are in terms of what do we mean by early detection and diagnosis. So I have to confess, when I joined AI UK, I got quite a lot of grief for getting the two mixed up. So dementia, you all know this, is a set of symptoms. And dementia is caused by diseases. Alzheimer's is the most common one of those diseases. We talk about detection as the ability to detect the presence of that disease, the first changes that are happening in the brain. Diagnosis is when a clinician takes all of those facts and makes a clinical judgment on an individual as we move forward. So at the moment, someone glibly put it to me, most dementias are diagnosed by accident, literally when there is an accident or a catastrophic trigger event. And then we go out and we ask the question, we say, what's causing it? We have got to change that radically over the next few years. We have got to start diagnosing the diseases that cause dementia before the dementia symptoms start, and that's the only way the treatments are going to help do it. Now, we don't need AI to diagnose dementia, but we do need AI and machine learning to help us detect the diseases that cause dementia. And when we look at this, David talked about this in a slightly different way in cancer. There are two really, what I'd say, real competing technologies at the moment pushing forward into early detection. One of which is pathology. So amyloid and tau in the brain cause tangles, which cause the dementias, which move forward. The latest drugs that you're hearing about are all about stripping the amyloid out of the brain. Blood tests are coming through. At the moment, we're looking at PET scans and quite intrusive lumbar punctures to detect the presence of amyloid in the bloods and in the brains. Blood's coming through. Cognitive function is the other area that's a sort of, I wouldn't quite call it a competing technology because they're complementary, they tell us different things. Cognitive function tells you when the brain is starting to change the way it works. And that's measuring things like working memory, episodic memory, executive function, and all of those kind of areas. Speech, language are coming through quickly. And then you layer on top of that the genetic risks that are coming through. just a bit of a journey really in terms of where we are actually in the clinic and what's actually happening in the clinics around the world as we go forward. I have randomly chosen a couple of examples from some of our landscape studies that have come through. Paper to digital to AI, that's the journey that we're on. The figure you can see there is a clock test. It's a well-established test for dementia. Can you draw a circle? Can you put the numbers on it? Can you put the time in it that does it? What particularly companies like Linus Health are doing is they start on the journey. First of all, you start with, okay, remove the paper. Let's have a keyboard entry. Let's have a tablet entry. Then you move on to, can we get the AI and the machine learning to reproduce what a decent clinician can do? Can it look at that and say the numbers are in the wrong order and save the clinician's time? That's great. And I think as David put it so eloquently, what we all want to do is to move on to the next step, to spot the patterns in those kind of tests that the clinicians can't yet spot, that are too subtle. The other thing that AI is really starting to enable is voice and language models, the ability to strip large amounts of data, extract features and put them in. So things like the Alzheimer's disease Discovery Foundation, their speech consortium, the quote from people like Winterlight Labs and Cambridge Cognition, monitoring cognitive impairment through speech and language change. And a lot of these tests at the moment, they're still in R&D, they're still in clinical trials, but they'll be looking to move into kind of clinical usage soon. I'm an engineer. It all starts with, can we measure the right kind of data and can we get the right kind of clinically meaningful data? I have no confidence in the ability of AI just to monitor what I'm doing on a day-to-day basis and then phone me up on the day and tell me that I've got dementia. It's all about clinically meaningful data. And this from our Eden project, the early detection of neurodegenerative diseases, this is our list. And it starts with a really strong cognitive test right in the middle of it that's measuring all of the different aspects of memory. And then we start looking at it and we say, actually, if we put things like gait, sleep, social activity, mood, eye movements, EEG, and layer those on the top, can we make those cognitive tests more sensitive and more specific? I think if any of you have relatives, friends with dementia, with Alzheimer's, you'll know that all of these measures change in people as they go through. And they change quite progressively and quite slowly. With hindsight and with retrospect, most people can look back at some of these measures and say, I could see that changing in my father, my mother, my auntie, whatever it is. And really the challenge we set ourselves is how early can we detect those subtle signs? So really, I mean, the questions are sort of, we're looking at it, specificity. Sensitivity, can we get better than the clinicians as we move forward on those ones? I think I just wanted to share, this is kind of a couple of slides that we shared with our board, courtesy of Zoe Courtesy and at Cambridge University. I know we've got a couple of the MPL scientists as well who are working on the same work in the audience here. Looking at AI models, what we're looking at when we build the AI models, we start with, think of those time steps as somebody going into a clinic and having a series of tests, scans, blood tests, memory tests. We'll then compare that with what the digital tests are telling us at the same time and build those and look for the clusters. The ultimate goal is to get away with the highly intrusive scans and testing and just rely on the digital markers, identify where people have got a problem, and then push them back into the system. Now, I think as we start looking at this is the kind of the ideal for us. What we really want to be able to do is to look at an individual, carry out a series of tests, complement it with some of the sort of lifestyle tracking and those kind of issues, and really try and plot their trajectory of cognitive decline. And across here we've got MMSE, which is a measure of cognitive decline. And this is where Zoe and the team have really managed to sort of cluster things out and look for it. So up at the top, score of 30 is the maximum you can score on MSE for cognitive function. Up at the top, nice, normal, healthy aging, And then we get a few other factors coming in. Down at the bottom, you can see a trajectory which is, for an individual, dropping down, showing significant cognitive decline. Typically around 24 is regarded as kind of cognitively normal. Now, so you can all of a sudden, I mean, you're all looking at this going, God, those data boundaries are huge, and they are. The real challenge we've got with all of this is the population diversity that we have to deal with. How can we really look at models which are going to separate out the really complex entanglement of geriatric depression and cognitive decline, that are going to look at people's their early years education, all of those kind of things, and separate them out. It's a huge task that we've all got ahead of us. Early days, and even if we could do this, I mean, we look at this stuff, even if we could actually say to an individual and look at a couple of tests, 6 months at a time, you're on this trajectory, we want to do it, we're not going to act without understanding the pathology again. You look at the lecanemab as a drug, the side effects are not insignificant. It's very expensive. You're not going to hand that out to somebody on the premise of just a digital test. You're going to want to know there's a build-up in amyloid. You want to know that the target's there in the pathology to strip it out. The biggest challenge, I mean, for me, as ever, it's all about data. It's all about practicalities. I tried to draw up a simplified technology stack to explain some of the challenges that we have moving forward. This is about as simple as I could get it. So if we kind of talk through, you start with what do you want to measure, who do you want to measure that in, who are the at-risk groups, which for something like Alzheimer's, we know that's quite a tight kind of age range coming through. You start with how are you then going to measure those data and extract them? We're working with Masurio. It's an active test app. I glibly put it, pictures of chickens. Have you seen this chicken before? Swipe left, swipe right. Did we ask you to swipe up? We're also working with a passive test app, which is longevity by applied cognition, and that's looking at sort of how you use the machine. Do you dwell on tasks too long? Do you look at websites too long? Do you have to go back and reread things? And it's monitoring all of that passively in the background, and supplement that with things like activity trackers, which are tracking disturbed sleep and all of those kind of issues. And then we need a secure data platform to put it, to strip it out, to do all the harmonization, the pseudonymization. That's all happening at the Alan Turing Institute. And all of that you've got to go through before you even hand it over to a machine learning expert and ask them to try and extract all the clinically meaningful data. It's quite a challenge. And then probably even harder at the back end, which we've not even started thinking about, how do you then cascade that out to your clinical audience in an explainable way? And data is the challenge. Data is a real challenge as we move forward here. How much data do you need to really build unbiased AI models? Quite a lot of the companies, particularly startups, are working with small data sets. And we all know that small data sets risk inducing bias. And we can't afford to do that in dementia. So black and ethnic minorities, women are significantly more at risk of dementia than the general population, and are yet really underrepresented in research. So we can't afford to make the biases any worse. And that's why initiatives like the ADDI data sharing, global data sharing platforms are really so important to actually be able to scale up the amount of data so we can properly train these things. And we've got to get this right. I think one of David's questions was, I've broken it. One of David's questions was, do people really want to know? Our studies in Alzheimer's and dementia say yes, people really do want to know. 74% of the population say they want an early diagnosis. 38% would say they would like to know 15 years beforehand, so they can plan for things, so they can get things ready. And I think, so that's why it's so important that we do get this right. Because if we don't have appropriate regulation, if we don't have appropriately trained models, they will go looking for answers in wellness apps, and they will clog up all of the clinics. We'll have clinics full of the worried well, so we've got to get this right. We want to revolutionize the way we treat Alzheimer's. Okay? Early detection is the key to that revolution moving forward. AI, machine learning are the key to unlocking the power of early detection. And large amounts of well-characterized patient data are absolutely essential to build AI models that are unbiased and population representative. And that's where we need to start. Thank you. I'm very sorry.
Right. Yeah, we've got a. Hang on a sec. We're going to pause for a slight technical adjustment. And while Gavin does that, I will introduce our next speaker, Jessica Morley, who's a researcher at the University of Oxford, working in the Bennett Institute there on health data, helping to develop AI-based clinical decision support software. Before that, she worked in the Department of Health and Social Care and was heavily involved in the government's Goldacre review. So, Jessica, and then let's give you the 30 seconds. We're making progress. We're just, pause for 30 seconds. So we seem to be getting back into business. Yes?
It was a very low-tech problem. I plugged my laptop in and didn't turn the power on, and I ran out of power. It is, there's only so much you can do.
Yeah. It's actually very helpful because I'm going to talk about hardware and databases.
Are we all right?
It's a bit slow.
Uh-huh.
Okay.
Right.
Come on.
Right, we're getting into business.
It will open eventually. Come on. Oh, for goodness sake.
And I apologise to our people participating online. I started registering the Q&As coming in, but we will be with you back in service in a moment.
Just check what that is. Yeah, we are.
I mean, the alternative is for Jessica to start. Do you want to take this off and get this?
Yeah.
I can just speak without slides.
Yeah, Jessica is wonderful.
It's just not loading very quickly.
I can just put mine.
We're there.
All right, okay, we're in business. It looks like we are getting there.
Yeah, just there you go.
Here we are. Fantastic. Jessica, you're good. We're very grateful to you for being so tolerant. Apologise for that interruption of service. A reminder that the most sophisticated AI ultimately depends on electricity supply. Nothing would be functioning without it. So,
There we go.
Jessica, over to you. Thank you for being so tolerant.
No problem. Right. Hi, everyone. Thank you for having me. And now I'm going to apologise because my main job, I think, is now to depress you by basically talking about how hard it is to get all of this stuff right in practice. So what I'm going to try and do is set a little bit of context as to why the NHS wants to be making better use of these types of technologies for early prevention. And then I'm going to talk about all of the stuff that we just heard about in that second part of the pipeline. So essentially, why is all of this working in research? It's in the lab, but it's not necessarily working in the clinic. And that's where we're going to get depressed. But what I'm going to say is that my colleague said at the start that he was an optimist. I describe myself as a skeptical optimist. I think we can do it, and I think there's potential, but I think it's really, really, really hard, and we shouldn't get so carried away and forget to think about the basics. So first of all, why? See, I told you, depression. Because the healthcare system is struggling. We know that the healthcare system is struggling. This is an undeniable fact. It's not even a particularly political thing to say. That number, 910 million, that was the deficit prior to COVID of the healthcare system. So you can now imagine quite how much that is now struggling. And this is a little data tracker of the waiting list that we all know is sort of skyrocketing now. So why is this linked to early prevention and detection of the disease? Because of this thing, it's called the triple aim. I should say that, especially on a day when our junior doctors are striking, that sometimes people expand this to four aims, which I will tell you about in a second. But the triple aim is to somehow achieve magic, which is improve the population's health, improve the experience of care, and reduce the per capita cost at the same time. The fourth one, that people then tag on as if it's an afterthought, is that it's improving the experience of clinicians. So basically make sure that clinicians have a nicer life as well, but it doesn't fit so quite well into this triangle. So then, what do? Well, we rely on this thing called P4 medicine. So medicine that is predictive, preventative, personalised, and participatory. This essentially means monitor everything about your life in data all the time, run an algorithm, some algorithms over the top, find out what your personal risk is, do personalised risk stratification, then target the drugs that we want to treat you with, and provide you with personalised earlier levels of intervention. The idea being that that simultaneously reduces cost because it's early, it's basically cheaper to treat people earlier than late, or to prevent people from getting sick. It's better if you have a better experience of care, if we give you treatments that work for you better and that we're targeting you to you personally, and that ultimately this hopefully improves the population's health. So this is why we start seeing statements like this that appear in all kinds of UK policy documents at the moment. So this is from the Future of UK Clinical Research. Our vision is for the UK to have the most advanced and data-enabled clinical research environment in the world, where we capitalise on our unique data assets to deliver improvements to the health and care of patients across the UK and beyond. Because apparently we're all Buzz Lightyear now. Or we have, by 2030, the UK has a learning health and care system. So this is the idea that data is circulating around the healthcare system the whole entire time, not only improving our ability to diagnose individual patients earlier, but also improving our ability to monitor the overarching performance of the healthcare system, to deliver better outcomes enabled by the effective use of AI. And this one is, again, from the life sciences vision. We will seize the opportunities to support the NHS and patients through innovative NHS data partnerships that fundamentally drive improvements in our health and care outcomes and or reduce health inequalities. I would quite like the or not to be there, but it is there. So, enter clinical decision support software. So it's all very well and good to have people like me sit in a university building, write a model that can predict when people are going to develop diseases, but how do I actually get that into the point of care? So this is where we have clinical decision support software. Now, clinical decision support software sounds kind of fancy. It's actually existed since the 80s, and I should also remind people that AI is not that new. The first paper published promoting the idea that AI might help with diagnosing diseases, 1959. So we have been trying to get this right for a long time. But clinical decision support software does exist. It does exist in the NHS. It has existed in the NHS since about 1980s, but it's not very smart. What you get is little pop-ups that are basically based on flowcharts, if this, then that types of scenarios. So if I go to my GP, for example, there will probably be a little pop-up that appears in the electronic health record system that says, hey, Jess is female, she's over 25, you should probably remind her to go to cervical screening. And then I won't go. But the pop-up will appear and tell me that that's what I'm supposed to do. That's not particularly sophisticated. What we are actually talking about is trying to do models that do all of the things that you've heard from my wonderful colleagues already. So this was a model that my group built to predict risk associated with COVID. It was the largest COVID study and still is the largest COVID study done to date. We did it on 58 million patient records in the UK. And this is essentially the thing that looks like Star Wars. That's measuring all of your different hazard ratios compared to different people in the population. So compared to the baseline, and this baseline thing is important to remember for reasons that I'll come on to later, how much more likely are you to have experienced negative outcomes from COVID or severe outcomes from COVID. That then get deployed as the shielding list. So there's everybody's letters get sent to say, please, can you shield? And then ultimately it was used to roll out the vaccine program. So this is talking about clinical decision support because it's a model, it's an algorithm predicting risk, therefore trying to intervene earlier, prevention, and then deployed at the point of care. But wait! The NHS, every time the NHS tries to do very large transformations of technology on this scale, it tends to go quite badly wrong. And the government also tends to get stuff a little bit wrong. So we have had this thing called AI winters. This is where we have gone in the past several times, AI is going to save the world, and then the reality does not quite meet up to the expectations, the investment plummets, and then nothing happens. And similarly, we haven't had a great track record of actually implementing tech into the NHS. So this is the NHS NP-FIT, a National Health IT Plan, the biggest IT or public sector IT transformation program in the world. It did deliver some great things. It sometimes gets a bad rep. It did deliver the NHS spine, which we couldn't do any of the stuff that we're talking about now without the spine, but it also cost a lot of money with not fantastic outcomes. And then when we've tried to do things with data, they've also gone wrong. So people might remember care.data from 2013 to 2016, and the more recent, very confusingly named GPDPR, or General Practice Data for Planning and Research. Both times we tried to say we're going to put all of the NHS records or GP records in one place to enable easier access for research. Drastically damaged the public trust, and now we have an opt-out rate offering about 6%, which is really, really problematic for all of these types of science that we're talking about. And then Royal Free and DeepMind. So people who may remember this is DeepMind and the Royal Free tried to develop and did successfully develop an app called Streams, which early alerts clinicians to people who are going to get acute kidney injury. But in the process, they misinterpreted data protection law. So very simply, data protection law splits use categories into two. So it's either direct care or it's research, and then there's service analytics on the side. If it's direct care, that's if my doctor wants to talk to another doctor, you don't need patient consent in the middle of that to transfer the records. If it's for research, you do need patient consent. Now, the Royal Free thought that because they were developing the app to be used in the hospital, it fell under direct care. Actually, it fell under research, and so they had handed over many thousands of patient records without consent, and they broke the law. So should we quit? No, the NHS should not quit. It's in the NHS's constitution that we are committed to supporting innovation when we have the potential to save lives. And we know we have the potential to save lives. We've heard it. But basically, it's just really complicated. If anybody can remember Facebook back in the day when it used to ask you for your relationship status, then this is the NHS and the healthcare. It's complicated. In fact, it's complex. So this is a model, which I won't bore you with, but essentially it says in each of these 7 domains, from condition all the way through adaptation over time, the more complexity there is in each of those domains, the more likely it is that the technology is to fail. Now, AI hits complex in every single one of these. It's complex in the condition because we're not trying to deal with just one type of condition. We're trying to personally screen everybody for every possible condition at all times. And it's really complex in embedding and adaptation over time because it changes over time. So technology, it's really, really, really difficult. As we have seen this evening, hardware doesn't always work. Data quality issues can arise. We've heard colleagues mention, for example, that data, most of the population is not particularly well represented in our healthcare data. And very often, the NHS's mission gets presented as we have the best healthcare data in the world. And we do, but it's not just there for plucking. You have to do a lot of work to make it work first, and then you've got to integrate it into clinical systems. You have to get it through procurement. You have to pass data protection. All of these have to happen, and it all goes wrong. And then there's the risks of re-ontologizing. That's a big, scary sounding word that I have to use because I come from the University of Oxford, and if I don't sound like I'm using long words, people might kick me out. But essentially, it means fundamentally transforming the healthcare service into a way that we might not want. And so AI has the potential to change what counts as knowledge about the body. This is because AI fundamentally measures things that we can record quantitatively. So people who have been to the doctor, yes, you might monitor your heart rate, they might monitor how many steps you take, they might monitor how much you sleep, how much you move. I saw one recently that was monitoring how many times you go and open the fridge. But it cannot tell you, and it cannot measure how you feel. And what your outcomes are, and if your mood has changed. All of these types of things we know matter just as much about people's healthcare. And often if people go to the doctor when they just don't feel like themselves, and that's your sort of first early indicator. AI cannot measure that because it's not quantitative. And so are we now then saying, oh, we only care about the stuff that appears in the signal in the data. We don't actually care about the stuff that you tell us about as a person. And therefore, it's changing who has the right to say that they have knowledge about the body, the algorithm or the person. Because now algorithms are not actually working on the individual themselves. They are working on the data clone of themselves. And that data clone might not accurately represent the person and their physical body. The therapeutic relationship. This, again, sounds a little bit airy-fairy, but we know that healthcare matters as much about the dynamic between a patient and a clinician as it does about the care that they get. So whether or not you have a decent, trusting relationship with your clinician, whether that clinician is empathetic, whether you feel as though there is trust in there, all of that stuff is measurably important and impactful. But AI cannot replicate it. AIs do not have what we call semantic understanding. They aren't humans. So we can teach a large language model to mimic an empathetic sounding human, but it will never understand what that actually means. And we don't know why that matters in terms of health outcomes. We just know that it does. And then there's this thing about the relationships between the body, the culture, and society. So we know that the way that we have dealt with medical ethics in the past, so bioethic principles, autonomy, beneficence, non-maleficence, justice, which is basically the broken down version of do no harm, have developed to help us understand how do we deal with a one-on-one relationship when we're giving somebody a drug or we're intervening directly with their body. So how do I, as a clinician, make sure I do nothing to hurt this one person, my body? AI doesn't work like that. It works on the group level. So if we go back to the beginning when I said that this is all about personalized medicine, it's actually stratification. So it's similar to targeted advertising, targeted intervention at a screening level. Now, if we don't get that right for every single group, we start to drastically change whether or not we can genuinely claim that the NHS is for everybody. Not everybody is equally represented in data sets. Not everybody will become equally represented in data sets. Not everybody has access to the latest smartphones, the latest devices. People who don't have a fixed address might not necessarily appear in electronic health records as much. They are still equally as deserving of our care. And importantly, there's this thing where we say we want to empower people with their data. We want to give them their data and they will be empowered to take better care of themselves. Now, the trick with the word empowerment is it's shifting of responsibility. So it's shifting from me, the healthcare system, to you, the person. If you are a person who has access to your data and you can take care of your health and you don't do it, well, then you get sick. Who's responsible for that? And so that shifts that relationship between the body, the culture, and society. So this is basically why it's really hard. So what I am going to say as my sort of fining thing is that while we are moving towards this beautiful future where we have AI helping us to prevent disease earlier, we should be focusing on these things to do with information and utility. So does it do something useful? Is it screening for the reasons that we've heard today? Screening for something that we can actually treat and we can actually help, and it's something that the system wants. Is it usable? Can the clinician actually run it in a clinic and understand what it says? Is it effective? Does it actually work? Because this is the big secret about AI. At the moment, it's very precise and it's very accurate, but we have almost no evidence that it can improve outcomes in the real world. And do people trust it? If we can answer those 4 things, then we'll have success. If we cannot, we will not. And that's me. Thanks.
Thank you very much indeed, Jessica. That was very interesting and very stimulating. Now, our fourth speaker is Tobias Rijken, who is a co-founder and CTO of Kheiron Medical, developing AI cancer diagnostics. I think Kheiron's breast screening solution is already helping doctors improve breast cancer detection, and we very much look forward, Tobias, to your observations on this. Over to you.
Great. It's a pleasure to be here, and I'm humbled to follow the great speakers because I'll definitely be borrowing some of your frameworks and concepts in my talk. So I want to talk a little bit about the work we've been doing on early detection of breast cancer using AI. And really, our motivator here is that we want to give every woman a better fighting chance against breast cancer. And we do that through screening. But maybe before I dive in, I want to start with a visual. I'm a very computer vision expert, very visual person, so let's start there. And this is a story of a specific case that was given to us by the professor who actually invented breast cancer screening, Professor Laszlo Tabar. And this was one of his hardest cases. This is a woman who actually ended up dying because of breast cancer. But she could have been saved if her cancer was diagnosed earlier and detected earlier. And basically, what you see here on the left is a very difficult case because it's a very dense breast. But MIA, our technology, found this cancer in the scan that the radiologist detected it in, but also the scan 2 years prior and the interval before that. So this woman could have received treatment 4 years before the actual detection. So the way that we think about cancer is it's an information problem. And along the entire cancer pathway, there are plenty of information problems. Can we detect the cancer in the first place? How do you diagnose and stage? What is the best treatment plan? And even when you're doing the treatment, how do you know that the treatment has a high efficacy? And because you need to keep doing the check-ins going on. And then at some point, this person is maybe healthy again, but then you start again from back because the cancer can reoccur, etc. So we thought, okay, let's start at the start of this funnel, which is detection, because that's step number one. You need to detect the cancer before you can do anything else. And we started with breast cancer screening, and I'll borrow David's framework here. The reason why we started with breast cancer screening is because it's very, very well defined. It's one of the best defined screening programs we have today. Who do we screen? Women between the ages of 50 and 75, maybe some countries 45, but it's at least very well defined. How do we screen? Mammography every 2 or 3 years, but it's imaging based. And what do we look for? Very well defined. How you then treat that, that's a question for later. But we thought if we want to introduce AI into clinical workflow, let's try and keep everything else as much as possible the same and help really where the need is. And the big problem in breast cancer screening is there's a huge workforce crisis. I mean, nobody will be surprised to hear that the NHS has a workforce crisis, but this is actually from a couple of days ago. The Royal College of Radiologists every year publishes a report about sort of the workforce. And this year the report said it's a ticking time bomb. There's already 30% of a shortfall in clinical radiologists going to increase to 40%. 50% of the vacancies are open for more than 12 months. And at the moment, we're spending $250 million a year just to pay for overtime and outsourcing. We're flying Dutch radiologists from the Netherlands for a weekend of breast cancer screening, pay them 4 or 5 times what we pay an NHS radiologist. And at some point, this is going to fall apart. And this is where we believe AI can help. So again, an example, essentially what MIA does is, because the breast cancer task for radiologists is so well defined, we want to focus on solving exactly that task. And it's a binary question. The radiologist needs to answer the question, should we call back this woman back for further examination, yes or no? There's no diagnosis here, this is detection. So is there a cancer here, yes or no? And that's an easy question in the vast majority of the cases, because this is a low prevalence regime. 1% of women in a screening population has breast cancer, the other 99% are healthy, and maybe 10% of those are the hard cases, and those are the ones that matter. So on the left side is an example of a very difficult positive. The doctors missed it, and Mia found it. But actually, when you ask a screening radiologist, they get excited about, show me the difficult negatives, because these are the ones that lead to high false positive rates. So show me that you can work well on those. So this is a case where actually the doctors called this back because they thought there's a cancer here, or at least it's too difficult, let's do some follow-up imaging. And Mia correctly said, no, this is fine, this is healthy. By doing that task, we thought, okay, how can you actually bring AI into the workflow in the most natural way? And because we do the same task that the radiologist does, we can be very flexible in our workflow. So on the top left corner, you see the current standard of care, which is double reading. So every mammogram is read by 2 radiologists. When they agree with each other, great, you do whatever they agree on. When they disagree, you call in an arbitrator radiologist. This is incredibly wasteful workflow because, as I said earlier, these 2 radiologists agree on the 90% of cases that are easy. And that's almost 2 million women per year, every year, that are read by 2 radiologists. Those are the easy cases. Where we want to get to is a scenario where Mia becomes one of those readers, because then we can say 50% of all the reads all in one go. We also identified that actually when you add another arbitration step, we can increase the cancer detection rate. And that's something that we're now starting to see the clinical evidence of. We tested that in Hungary. That was picked up by New York Times. And this is something that we believe can be introduced in the NHS in a very sort of low-risk way. That's essentially the workflow at the top right, because we're not changing the standard of care here. You still have the 2 human radiologists in the loop. There's still an arbitrator. We just add Mia as an additional step. And that can at least help identify some cancers earlier. So getting AI into clinical practice is hard, very, very hard. I think we've had some success getting it there. There's still a long road ahead, but where we are today, we won one of the UK government's AI awards to get Mia adopted in the NHS. It's already being used in Aberdeen as a service evaluation. We're starting one of the first UK prospective studies, and we're currently deploying in 15 screening units, which is the equivalent of 25% of UK screening volume. So by the end of the year, we want to be screening 500,000 women per year in the UK to try and help find their cancers earlier. We talked about this a little bit in previous chats, but its generalizability is key, and making sure that Mia works for every woman everywhere in an unbiased way is super important for us. So basically what we mean by generalizability is when you develop an AI model, you do that on a data set, but really what you want is that the AI works well on future data that you haven't seen before. Now, the problem becomes if you train your AI on a very biased data set or a small data set that's not representative of the general population, then your AI will not generalize. So what we did early on is build one of the largest data sets in breast cancer screening. That's a grind. It took a lot of work, a lot of collaborations, but essentially we optimized for not having the largest data set necessarily, but also one of the most diverse data sets. So our data come from the UK, Europe, Asia, South America, North America, different genetic makeups, different hardware devices with different post-processing softwares, even different screening programs, because the kind of screening program that you have in a country, whether it's a 1-year interval or a 3-year interval, will determine the distribution of the sizes of cancers, which in turn can determine the performance of your models. Hence, all these factors that you need to take into account when you build your data set. It's a lot of hard work, and at the moment, I think that's the way you have to do it. So we showed the results on a very large retrospective study, 275,000 cases, unenriched, so we did not sub-sample the data set, we just sampled everyone in the data set, including those cases where you don't yet have the follow-up. And this is very important, because how do you know whether your AI is right in predicting cancer? You need to know whether the end outcome was cancerous or not. The problem is in breast cancer screening, there's a delay in those outcomes, because biopsy results typically take a couple of months to get. And in order to truly be able to say that the cancer is negative, you need to wait for the next screening interval to find that negative case. But that means there's always a set of cases where you do not have ground truth. That means you can't ignore those cases, because these are still part of your data distribution. So those we've all left in. And we've done this across a number of different countries. As I said, the key is that we build AI that works for every woman everywhere. Specifically, an area of focus for us is breast density. So breast density is actually a risk factor. African American women have a slightly higher risk of being diagnosed with breast cancer, and we are working specifically with Emory University, which we selected for this reason because they have a large African American population, and we're now testing how well the AI generalizes, and those first results are looking good. Now, the story doesn't end when the AI is deployed. That's actually just the beginning. We've done all the academic and clinical validation, but what do you do when the AI is actually there? AI and data are not stationary. It changes all the time. Data changes all the time. And those changes in the data might affect how your AI performs, and that's not necessarily a problem as long as you can monitor this and act on it. So an interesting example was COVID, because we were already running live before the pandemic, and then one day to the next, the NHS decided to stop screening for breast cancer. Now, when you stop screening women, that doesn't mean that their cancer stops growing. So a couple of months later, when screening programs got reopened, we noticed that our AI started behaving differently. It started calling back more women, not just us, but also the radiologist. And that was completely natural to us because the cancers had more time to grow and the distribution had changed. The cancers were now bigger, and we could actually detect that with our monitoring. So an AI system is more than just an AI model. It is a system that consists of the model itself, hardware to do the inference, but also modules around the model that help you detect, is this data representative of the data that I trained it on? Are the outputs along the lines of what I expect? And are there other kind of models that we can put in place that help detect with drift or bias or quality of the image? And just one of those examples of monitoring tools that we have built is we noticed that one specific hospital overnight reported a completely different change in the number of cancers that was a number of women that was called back. And then we went back and we realized, hey, did something change on this date? And the hardware vendor for this hospital had upgraded their post-processing software. And they hadn't told the radiologist and the hospital about this. We told the radiologist, hey, something has changed. Now, the tools that we built, we could basically recalibrate the model quite quickly. And as you see in the slide, we got back to the same level of performance very quickly. But you need to be aware of every step between the image acquisition and the data before it goes into your model. And anything that can affect that, you need to be able to monitor. And this is not a problem that's unique to us. We tested the same model on histopathology, and luckily this transferred. But being able to detect changes to the data or your model in real time is absolutely critical to make sure that we keep deploying AI safely. So where are we now? I think there's a lot of evidence right now that in our specific use case, AI works well. But again, bringing this into in clinical practice is hard. There's no clear path to adoption at the moment, and this is a multidisciplinary problem. This is not just a technical problem to be solved. There is a question, okay, who pays, what's the health economic benefit, et cetera. And that's sort of our next set of challenges. And thank you very much.
Very good. So our panelists want to come and take their place up here. That would be fantastic. Great. Good. And I'm going to take sort of chairman's prerogative, and if I may ask the first question, which I think follows on from the presentations, which is that for lay people, we think of the advances in AI as being driven by applying enormous computing power to very large data sets, and that's how these large language models, generative AI, have been emerging. There are some people who think if there's any area where the UK has any kind of comparative advantage, it is our healthcare data set. So if we're to apply AI in healthcare, perhaps the UK does have an opportunity here. Now, and it would be interesting to know, Jessica touched on this in your remarks, that although theoretically we have this, in reality it's very hard to do. Tobias, you clearly have been accessing very large data sets, of which the UK was one, and so you've been able successfully to access data sets from a range of countries. So does the UK and its extraordinary NHS patient data, which in theory enables us to link so much information about people's medical history in a way few systems can, do we have a comparative advantage there, and do you envisage that as enabling the UK having therefore some particular role in the application of AI to healthcare? Jessica, you touched on it and said it was all very difficult. So you're a sceptical optimist. Are you particularly sceptical or particularly optimistic about that one?
Depends on the day and my mood. But so I also think it's important to differentiate between different types of data. So imaging data and there's electronic health record data. So imaging data has a slight advantage in that it's far more standardized and more structured than electronic health record data is. Electronic health record data is richer, so there's more information in it. And so that's where we can get more big complex models like some of the stuff that I was talking about. Do we have an advantage? Sort of simultaneously, yes and no. We do because we have longitudinal health records, so we have people's records going back to birth. We also have a large population and we have a fairly diverse population. We have a disadvantage in that we went quite quickly, so the NHS digitized records fairly early on from about the 1970s and then in a really big push from the 1990s. So 98% of GP records were digitized by 1996. The issue is that that's now all legacy systems, and also people didn't start doing that with the intention that the data would be used for anything more than an aid memoir for clinicians in the future. So then if you were to compare that to places like Estonia, where they have a smaller and less diverse population and not necessarily the longitudinal health records, but they don't have the same legacy IT infrastructure that we do, then you can sort of balance it out. So to give an example, because sometimes I think this stuff sounds hyper-theoretical, when we were doing the model that was to do with COVID, we kept getting a lot of results of men who were in their 70s who were pregnant. And we're like, this doesn't, it turns out that the SNOMED code, the clinical code for fetus and for dodgy knee, is really similar. So bunch of clinicians who were tired trying to code that this person has a sore knee had actually given them a fetus. Same with things like pregnancy. Pregnancy was a big problem in COVID. Do we or do we not vaccinate pregnant women? There's no SNOMED code for no longer being pregnant. So basically, unless you go and link for the record of the child, the woman or person will stay pregnant for forever. So there are lots and lots and lots of data quality issues. So this means that basically every time you do a data science project, I think the ABPI, so the Association of British Pharmaceutical Industries, said 80% of all of the work is data curation before you even get to any of the sciencey bits. So that's why I said it's hard.
Tobias, you clearly have had some success. And it's interesting that for your company you have been able to access NHS data, but also from other countries. Compare your experience.
Yeah. I mean, as Jessica said, the nice thing about imaging data, that it's fairly structured, and there's not a lot of room for interpretation in the image. I mean, it's the image, you look at the pixels, it's there. I think for us, the big question was, can we, what we call reconstruct the patient timeline? We don't need identifiable data. It's all de-identified before we get it, but for us, the key is, can we reconstruct what happened to this woman? Because most of them actually don't have breast cancer. We don't call them patients, we call them clients or screening participants. But can we get the follow-on screening around so that we can establish that indeed there is no cancer? Or can we get the biopsy reports? So that's, I think, has been our biggest challenge. And actually, to be fair, in the NHS, that has been relatively well kept. The issues that we ran into are more practical, as in a certain trust did a database migration, a PACS migration, which is the big imaging database, and now all of the data from before 2018 was just gone. And these are the practical issues that we had to deal with. What we look at is also the data generative process, because what's important to be aware of is that the data that's there in itself already has some bias encoded, and that is the decision that you make to collect the data in the first place. You need to think about. So, for example, all the mammograms in the UK will come from women in a certain age range, because that's how we designed the screening program. The screening interval is 3 years as opposed to 2 years in Western Europe and 1 year in the US, which means that the distribution of the size of cancers and the stages of cancers in the UK is different from what you have in other countries. So it's very important to be aware of all those steps, or we call that the data generative process, before you reach the image, and model that before you actually start working on building your AI.
Yeah. David, you're also involved in cancer. Your observations on that?
Well, I suppose you asked if the UK has an advantage, and I think we potentially do, but we're in danger of blowing it. I think if you look at a health system like the States, so the disadvantage we have is a relatively small population. States is a relatively big one. But the advantage we have over them is the unified single system, whereas theirs is fragmented into lots of little tiny empires of insurance providers and individual hospital systems, each of which has their own set of records, their own kind of patient population. But the bigger ones of those, so you have the sort of Kaiser Permanente system on the west coast of the States, which is bigger than the UK by some significant degree. So we imagine ourselves having this one health system and this real big advantage, but it's not perhaps as big as we might think. Now, there are still barriers on the US side. Even within one insurance provider, you've got people moving providers, and so you lose them and they're gone from the system, whereas we have a lifelong system, as Tobias pointed out. So we've got all this potential, single system, lifelong, unique, NHS number, patient identifier, so you can track things over time. But so we've got a bunch of problems. Like, as we've heard, there are different kind of electronic health systems that are all quite old, that make things a little bit patchwork and fragmented. And one of the real things where we've managed to shoot ourselves in the foot a couple of times is the issue of public trust. And not wishing to criticise any previous government administrations, but I think the way that care.data and GDPR were handled was suboptimal in terms of not engaging with the public enough before trying to implement them. And there was backlash. There was backlash in the media. As Jessica said, the dropout rate, people now withdrawing their consent for the use of their data for research, has reached an all-time high. So public trust, communication, getting people on side is going to be the key to realising the potential of our health system as a data source.
Thanks. Mike?
I think on the data side of things, I think we should have an advantage, but I think from my point of view, I think the investment to join up all of the different data sets is huge. And I don't know at the moment whether there's a real appetite to dig into all of those ones. One of our advisors gave me a really interesting metaphor, and he was he came out of the NHS and NHS Digital, and he said when you look at the NHS, it looks like you're dealing with an enormous whale. You look at it from the top and you see this great big grey shape flowing underneath the water. When you actually probe into it, what you're dealing with is a shoal of fish. Every one of them with a different brain, every one with a different driver. They just happen to be moving in the same direction. And the way that you join those things up requires an enormous amount of investment. I think, as Jessica said, starting with things like the spine and cascading out, what we actually end up doing in engaging with it is looking for the early adopters, looking particularly where the secondary and the primary care are really well joined up and those kind of things, and looking for those early adopters, and then putting the innovation into those places, and then almost shaming the other parts of the NHS into adopting them. And I think that's the way it kind of works in practice at the moment. And I noticed with Tobias, the pilot was done up in Scotland, at Aberdeen. Presumably, again, an early adopter centre who kind of saw the advantage, get some publicity out of it, work with it. And I've no doubt there's a whole load of headlines flowing about being a postcode lottery and how people in Aberdeen are getting better treatment than people in Glasgow. But you're going to have to live with that, and you're just going to have to live with those kind of negative downsides.
Yes, so potentially in theory, but much harder to do in practice, and some wonderful examples of the difficulties of even just coding the data. Right, let's go collect some interventions here. Gavin is the man with the mic. Fantastic, we've got some interventions here, Gavin. Yeah, I'm going to collect several. Yeah, and if you could give your name and organisation, please.
Sheila Bird, formerly Medical Research Council's Biostatistics Unit in Cambridge. A key change that we need to make in England and Wales is legislation to end the late registration of fact of death. If a death is referred to the coroner for inquest, it is not registered with the Office for National Statistics until such time, weeks, months, or years later, the coroner determines the cause of death. The Royal Statistical Society has been campaigning since swine flu as part of our preparedness for the next pandemic, which of course was missed, that there should be legislation so that, as in Scotland, fact of death is registered within 8 days of death having occurred. Because whatever system you are looking at in terms of longitudinal follow-up, you want to know whether the data ceases because the individual ceased or because they were rehabilitated.
Right. Okay, so you can stay pregnant and you can also stay alive. Right.
And you can also die twice.
Right, yep.
Thank you very much. So Julia Sutcliffe, Chief Scientific Advisor at the Department for Business and Trade. Firstly, thank you for a really fascinating evening of presentations. I'm interested in some of the complexities you've talked about. You've talked about data, which we understand is a complex topic. You talked about advocacy and trust, etc. Where do standards fit in? I'm sort of interested that you talked about early adopters, different parts of the healthcare system deciding to early adopt, others deciding not to. How does standardization affect that, and how do we drive that sort of strategy rather than different parts of the system adopting when they feel like it, and almost having this kind of open market on our health data sets?
Right, and were there any more questions on that side of the room? Well, let's take a couple more on this side. Yep.
Related to that question of standardization is the one of regulation. And everybody has talked about interchangeable data being transferred between countries and across all sorts of borders. I'd be interested in your comments on the use of or how regulation is going to affect the use of AI in medicine, and in particular, obviously, the regulation that the UK may implement compared to our big market, if we're going to commercialise any of this, which is the USA.
Right, I'm going to pause there because I think there's a theme emerging, because all three questions were in a way about this regulatory issue. The first was asking for an improvement to the regulations, and then we're also hearing about to what extent we should standardise. David, why don't you start?
Thank you. So I agree that both regulation and standardisation are major challenges for this field, and I think that 5 or so years ago it was probably a bit of a wild west, but I think the regulators are kind of catching up and making major efforts to retool the way that they consider these technologies and how they classify them and how they evaluate them. What we don't yet have is the pathway we have for drugs, for example, where a new drug, there are very clear thresholds for evaluating its efficacy, whether it works. There are very clear thresholds and standards for evaluating whether the extent to which it works is worth the money that it costs. And there are formulae that are just there, and you hit that price threshold for delivering X amount of clinical benefit, you're in. And then once you're in, you're recommended by NICE, then you are adopted across the NHS. I'm not going to say seamlessly, but there's a process there and it happens. There is no such process for medical technologies, including AI. But we're working on it. I say we, it's nothing to do with me. The country is working on it. And the regulators are thinking about how best to evaluate these. The point that I'd make on standards is, I think I'm going to agree with Mike when he says that it's necessary for there to be early adopters. And if you wanted to standardise the adoption of a technology in the system to the extent that it's all or nothing, I'm afraid it would be nothing. Yeah. I'm afraid we would never get to a threshold where universal, instantaneous adoption was felt to be safe enough and affordable enough and effective enough. So I think we're going to need to be a little flexible, a little adventurous in how we early adopt and early implement some of these technologies in certain places as test beds. You know, does it work? Does it feel? Is it safe? Is it health economically practicable? And then roll out wider. Otherwise, we're in danger of kind of decision paralysis, and we'll never get anywhere.
I just want to add, before we go to Mike, I want to add one more question to the mix from one of our online participants, who I think does get to a key issue in the AI debate at the moment. How can a dynamic, constantly changing algorithm best be regulated? So we're talking about AI in healthcare, and regulation of AI, how you might set about it, is in itself incredibly tricky. Regulation in the NHS is incredibly tricky. Putting the two together, how do you make that happen? Mike, any observations you have on that?
I suppose my first after David said about, I thought you were an optimist, David, in terms of adopting. One of our board members gave me a statistic. 17 years is the average time for new technology to get adopted into the NHS. And if you think about that, 17 years compared with the speed of the technology and the way it's changing around here, I mean, so clearly we've got to kind of change something with it. It's good to see the MHRA looking at the innovative devices pipeline that's coming through, joining up people, trying to move things forward. That's, I think, really got to kind of focus on it. I was also sort of fascinated by Tobias's one because one of the things that when we first started talking to the MHRA, they basically said to us, well, you're going to have to freeze the algorithm and then have all your development in a different environment and then redo it and retest it and reapply and reaccredit it. So I'm really kind of encouraged by the fact that actually seems to be a route where you can monitor and track it and allow it to grow and learn. So that's really a big step forward even in the 2 years that we kind of have been working with the MHRA, so that's a good thing. I think there's a difference between standardisation and adoption, and I think you need to kind of separate all of those things. In terms of standardisation, I think the biggest challenge we have, particularly around cognitive assessment, is there are so many different measures of measuring cognitive assessment. There's no one really agreed term that's really been developed that can help you in the pre-dementia stages, the clinical sort of mild clinical impairment, subjective clinical impairment, prodromal state, and there's nothing in there at the moment. So that's a real big challenge that we'd have to do in terms of in terms of some of the standardisation moving forward, and that would really help, I think.
Right. Jessica?
So I think it's all sort of feeds into one. So first of all, that 17 years statistic gets bounded about a lot. I have tried to find the source of it and never been able to find it. So I have some questions about it. But at its root, it's actually, people tend to say that people explain it in a way that it's like it's bad, but it's fundamentally, it's because doctors do what is safe. So things take time to trickle through to get to know, yes, I trust this, yes, I think it will not hurt my patients, and that does take time because it takes time to develop the evidence base, and that evidence base does not yet exist for these types of technologies. So we have to be a bit skeptical there. But in terms of regulation and standardization, they all play roles. So to this lady's point, the data regulation is a complete mess. And so before we start talking about regulation of the AI, the data regulation is actually completely ludicrous. It makes no sense that in this world, we still have every single type of record is dealt with differently after the patient dies. So GP records are dealt with differently, hospital records are dealt with differently, they have different lengths of standards, they're held in different locations, they're controlled by different people. Then we have the fact that to this fish point, every single person in the NHS, individual organisation, is a different data controller. So that means for GP records, we have more than 7,000 data controllers. Now, that is really problematic because they make quite different decisions with regards to what goes on. And then this point I made before about the fact that we split use cases. Once you run an algorithm in a clinical decision support software type thing in a clinical system, you are blurring all of those use cases. So it's being used for clinical care, for direct care. It's research because it might be improving over time, and it's service analytics because it's in interpreting and changing the care pathway. So until we deal with any of that type of stuff and intervene with regulation and standardization at the data level, all of the stuff to do with the tech is almost immaterial because we'll never get there. Yes, medical device law, etc. I won't touch on so much because my colleagues have got more experience about that, and the adaptive algorithm I'll let Tobias talk about. But so I think standardization plays a role in data, but the problem is we have too many standards. So actually I think we need to get harder. We need to reduce the number of standards that exist, and we probably need to move to a regulation rather than standardization.
So, Tobias, we're realizing that you've been able to make progress because, in a way, your data is a very, if I may say so, small part of a wider person's medical history. Maybe even you have found dealing with this one item has been itself tricky. It'd be interesting to know how you found that and your reflections more widely on how it should be regulated.
Yeah, as I mentioned at the beginning of my talk, one of the things that we've done is why we started breast cancer screening as well is because it's so well defined. And we thought, let's make sure that we start in an area where we don't have to reinvent the entire field or how we bring this in. So much of breast cancer screening is already sort of cut out. And how do we fit into that was our big question. In terms of regulation, that was sort of a similar question. We worked with a regulatory consultant, and the answer was quite straightforward. You're a medical device. There's existing regulation for software as a medical device. We're a class 2A medical device, which sort of measures a trade-off between risk and benefit. So you do a clinical study, and then you get a CE mark, and then it can be used for an intended use. And it's all about the intended use. It's not the model per se that's regulated, although at the moment that is frozen, and if you want to make any change, you need to go through this whole process again. But it's the model and what do you want to use it for that's being regulated. So I think that has worked so far. It's not ideal for a software company because indeed it will take us about a year to get a new sort of CE mark, but our model iterations are happening on a monthly basis because we learn, we get more data, we improve the model. I think the second point is more that, as I said, AI it's not operating as a single model. And an AI product consists of a whole system. And there are all kinds of factors in that system that might change. It's either the data distribution that changes or other part of the data generating process. I mean, the hardware vendor that updated their post-processing software clearly had an effect on the algorithm. Of course, we are building our tools to make sure that the model is as robust as possible, but the clinicians need to be aware of how other parts of the system influences the AI. Right? Just changing the screening program will affect the AI, and we need to be aware of that. And so whether that needs to be regulated, I don't know. There's clearly a journey that we need to take clinicians and policymakers and stakeholders on to just understand all the different confounding factors that have an impact on AI.
Thank you. Let's collect some other interventions. Yes, there's a three on that side of the room. Yeah.
Thank you. Andrew Mackenzie from the Physiological Society. Very interesting presentations. Thank you. We've talked a lot about clinical use of medical devices. What about more consumer-facing products? There's obviously the regulatory route for medical devices, but what are the opportunities and risks for people to maybe make more informed decisions about their own health using AI models that maybe don't go through that same rigorous regulation route?
Thank you. And forward, yeah.
Thank you. Roger Kneeburn, Imperial College London. Excuse me. At one stage, well, in the 1980s and 90s, I was a GP and was involved in the early transfer of data from written records to early computers. And my question really is about trust, because I think at that time there was a sense that patients, with my patients, that they understood that there would be glitches, but that the system was inherently trustworthy. Now we hear so much about deep fakes and the sort of broader sense of AI being both a threat and an opportunity. And I wondered, looking at that, what your sense was about where the specific things that we've been talking about, screening and all those things, what do you think is likely to happen in the context of a changing relationship that moves away from unquestioning trust in a system to deep anxieties about whether it is actually trustworthy at all?
Yes, and then in front of you, yes.
Thank you. John Lowe, Institution of Mechanical Engineers, and also running an industrial museum, which is very strong on STEM. Lord Willetts, this is a question you've had many times, but I'm interested in the views of those at the coalface, the four speakers today, and it was articulated by Tobias, really, who noted the shortfall in skills coming forward, able to develop things. And whether those skills go into regulatory or into equipment or to the development of AI itself, we have a real problem in this country. There are a number of initiatives been running for many years, but we haven't moved the needle enough. We know some of the lessons that exposure of young people to STEM learning has to be fun, it has to be continuous, you can't just do it in a day, it has to be linked to real outputs and so on. I'd be very interested in the views of each four speakers. What the hell do we do to get STEM right, get youngsters interested again in science, technology, engineering and maths to help to resolve some of the difficulties that Tobias has articulated?
Thank you very much. So we've got three very different questions. Let's start with Tobias, and we'll work along the other way this time. So you've both got regulation and trust and skills.
Maybe on point.
You're not obliged to answer all three, by the way. One of the luxuries of taking them in groups is that you can pick which one you particularly feel moved to engage with.
Maybe let's start with the point of trust. I think there's two parts to that. It's like, how much can the users trust the algorithm? And that's, I think, in our opinion, where monitoring comes in. Because this is where the more you can understand how the AI behaves in real time, in the real world, in all kinds of different scenarios, and you can actually measure and monitor that, that will increase the trust that we can have in the devices. In terms of public trust, we actually, I think our experience is people have been quite positive and curious. So maybe to take an anecdote from the work we've been doing in Scotland, the Aberdeen study, that is under an opt-out system. So women, everyone in the screening system is participating, and people can opt out, and we have an opt-out helpline. In the first 2 weeks, we received a number of phone calls, I think in the end 15 or 20. And only one of those was to tell us that the lady wanted to opt out. The other 14 was to tell us how excited they were to participate in the study where they would be screened by AI. And that's, I think, in part because the workflow that we built was there's always still a human in the loop. Every image is still read by a human and an AI. And that's where I think we are also trying to build the skills with the radiologists. I think AI will not replace radiologists, but radiologists using AI will replace radiologists who don't. And so a large part of the work that we are doing is how do we educate the radiologists in the use of AI. It's actually a large part of our onboarding is training the radiologists in how to use the AI.
Yeah. By the way, I should have said, I think, Jessica, and we want to again give all of you these are your, I think as we're slightly overshooting, these are your concluding observations. And after this, we'll go and have a drink and compare notes. So any final observations you have to make? And I think on the trust question, you had this figure of, you said, I think 6% of people who were opting out, which didn't sound very high, but you said even that was significantly affecting the efficacy of the use of the data. So we might comment on that as well.
Sure. Okay, so a few things. I think, again, they are all sort of related. So to the consumer-facing point, I actually think it's a really big problem that that stuff is less well-regulated than a clinical thing. So to Tobias's point around medical device law being entirely predicated on intended use, at the moment there's all these symptom chatbots on the App Store, and they will all say on their App Store, this is not medical advice, and that's their way of skipping medical regulation. And that's a really big problem because a lot of the stuff that they present is nonsense. So there was one thing a little while ago that was telling people who are having a psychotic episode to drink liquor. Okay, I don't think that's inherently safe. And then when you think about the stuff that large language models, etc., that everybody's very excited about, they're trained on the internet. Have you ever been on the internet? Like, I think it's a problem. Where I do think, the topic that we haven't touched on is back-end operational efficiency. Everybody is very excited about the sexy stuff because it's like, oh, we can intervene with clinical stuff. I think we will get far better results for the NHS and to talk on things and trust if we focus on back-end operational efficiency. So things that can do note-taking, things that can monitor performance, things that can do rostering. Yeah. The point on trust and 6% is a high proportion of the population, but it's a particularly problem because it's non-random. Right. So it overlaps. Like there will be, for example, this is conjecture, but I suspect you would find it's true, that there's a significant overlap between the people who opt out of their data use and the people who are anti-vaccination. So you start to get these pockets of people who disappear, and you start causing problems. In terms of how we repair that and why it has happened, anybody who's interested in this stuff, please go and watch Cathy O'Neill's lectures about trust, but essentially she talks about the difference between passive and active trust. So we used to have a passive trust in the system because everybody understood what a doctor does, how a doctor is trained, and I go and I listen to the doctor and the doctor tells me what to do. Now we have to have a more active form of trust because there are so many players involved in the system. It's no longer just me and the doctor, it's everybody else is involved, and there's a complete lack of transparency and accountability over that. So nobody in the NHS can tell me where all of the data is flowing. We did a mapping exercise. Every single person's record in the country is going between 2 and 16 individual providers, and then that's a 1-to-many ratio on top of that. Now that is insane if I cannot then know what that has been used for. So there are now too many players, and we have to build accountability on top of that. In terms of STEM and how we make that exciting, link it to why it matters. I think sometimes people try and teach maths and science, etc., as if it's like an abstract thing. Young people today are motivated by social change and what happens, that climate change, healthcare, all of these things, they will be dealt with by maths and science. That's why we're all in this room. So don't make it an abstract concept, link it to the real world. There's a really excellent podcast I listen to called Breaking Math. This is really revealing quite how much of a nerd I am, but it talks about the mathematics of everyday life, and it's utterly brilliant for making you want to go out and do some calculations. Admittedly, that might just be me because I have no social life, but I think that's why you have to make it, link it to the real world. Yeah.
You should regard coming along to the FST as part of a rich social life. Mike, your comments on those themes?
Yes, that's part of my rich social life. I think I'd like to start really with the kind of the direct-to-consumer type question that I think it is, because particularly in the sort of dementia space, it's an area that's booming. Things like brain health apps, wellness apps, all of those kind of things. We've even got one of our own. It's quite a simple model at the moment. It's not yet AI enabled and those kind of things. But those ones, I think, as Jessica said, are sneaking underneath the radar. They're pushing stuff out with some of them very well-meaning, some of them not really thinking about it, but pushing out models which are based on very, very small data sets and hoovering up data from the people who will sign on to it. And of course, that's probably reinforcing more and more bias into the models because it's adopting it and all of those kind of things. And I think that's a real problem, and I think that's why we need to crack things like rapid regulation, innovation pathways for medical devices to get them into use really quickly. Because if we don't quickly roll out sort of tools that are trusted by clinicians, trusted by GPs, what we're actually in danger of seeing is a big risk of a whole load of people turning up saying, my phone says I've got Alzheimer's, what are you going to do about it, doctor? And that's going to waste an enormous amount of resources. Comes back to the skills thing that we've got. So I think we have to use these things to try and keep the worried well out of the clinic and focus on the people with the real challenges, the people at real risk, and draw them in. And we can only do that through real trusted regulation. And I think that's got to speed up. That's got to speed up quite a lot. Skills is an interesting one. I do actually think that sort of certainly in my kind of sort of working life, and particularly around getting people excited. I mean, excitement around climate change, excitement about electric vehicles, excitement about the future of flight is actually certainly inspiring my children to kind of move into engineering. And I think Jessica's right, that's the excitement. I also think that AI can get rid of some of the grunt work that we have to do through. The fact that Tobias is talking about, we're taking away, instead of having a radiologist who knows they're just sitting there doing a secondary check on things, that really starts to help free up some of the resources. AI tools that can mean that clinicians don't have to watch somebody drawing a clock to do that will actually free up in some of the skills and make you doing it. Radiologists, I mean, we all know about the shortage of radiologists, image scanning, those kind of things. I think those have the real ability to actually mean we can sort of address some of the skill shortages through technology. And I think, as Tobias put it really well, the people who can use and adopt the new technology will really start to shine. They won't be replaced. And that's going to lead to even more exciting careers with less grunt work as far as I can see.
Thank you very much, David.
I agree with what's been said. I think that on the issue of trust, I mean, at Cancer Research UK, we do a hell of a lot of engagement with patients and with the public. And what we see is not the kind of potentially the sort of reactionary fear of technology and change that one often hears about in the media. And essentially, I think that there's a kind of availability bias that, because we hear the bad stories about how people are afraid of, they don't trust the machines, they don't trust the system to keep hold of their data. Because we hear about those, then it sticks in our heads and it is available to us, and it sounds like a really big problem. I think if you systematically survey the population, actually, the majority of people like the idea of technology, they like the idea of scientific progress, they like being involved in research. The majority of people want their data to be used for research for the betterment of the healthcare system. And I think we need to remind ourselves of that. But the availability bias works the other way around as well, in that I think there will be trust in the medical system once it starts adopting AI, because people aren't communicating with the AI that's behind the scenes. They're still communicating with the doctors. And that's where they're getting their decisions and their input from. And there'll be inherent trust there, but it won't take much to break that trust. One or two high-profile fiascos, one or two women diagnosed with prostate cancer or whatever else that, the machine might accidentally throw out. That's all it'll take in the media, big hoo-ha, and that can really damage trust and really damage the way that we rapidly uptake and experiment with these technologies. So I suppose, a lot of this hinges on a hope that we might have more responsible kind of media reporting and storytelling that is contextualized in reality and the actual, event rates of true positives and false positives. But, like I said, I was an optimist.
Right, yeah. But let's not get carried away, Well, what a fantastic evening. Thank you very much to our 4 panelists. I think all of them did have a clear, optimistic message that all of them believe that in different ways AI has got the potential to make medical care better. I think that was actually a shared belief. But equally, we recognise there are some enormous obstacles. There's obstacles around the data and its reliability and accuracy. And feed rubbish in and you get rubbish out. There's also the take-up challenge and trust. So a healthy dose of realism as well. Thank you all very much indeed for participating here and also online, and thank you to our 4 panelists. Thank you very much.